All right. This is kind of a continuation to what I was just talking about with um you know I like uh basically that all the particles have mass, and what that really is just an attraction of energy. Uh and I think that photons do the same thing. And what I was trying to say in that one was basically that photons have like an innate function in them to do this, but you know they can't sustain it. That they're not self-sustaining. Eventually, the photon loses energy, but it can maintain it for a while. And so that's why light can travel so far in the vacuum. Vacuum being, space time, they can travel so far through space time because as they travel through space time, they are replenishing their energy, but the rate at which they replenish is not enough to um, keep them at their like uh, initial energy level. So, um, so um, particles are basically emitting photons as radiation, and this radiation is photons. And so I think that photons potentially are the tiniest um, particle we can get. Which, I mean, looking at things on a scale term, it does make sense because we consider them massless. So it makes sense that it would be the tiniest thing if we see them as a massless object. But um, I think that it's pretty much it's pretty much the bundling of photons that is um, potentially making up uh, everything that we've observed so far. I think that it could be that gluons are really just bundles of photons potentially, and quarks are just basically bundles of photons, and um, this would lead to a whole lot of questions. So maybe it doesn't make sense to kind of see it that way, and maybe I should just see them as, waste. It's a waste product. But I don't know. I don't. I don't know if that necessarily makes sense. It's definitely a waste product, but it doesn't necessarily mean that it is doing nothing. Um, but it's also hard to kind of understand what that is. Photons are basically particles' way of sending energy to someone else, right? So uh, maybe maybe there's more to it. Um, I don't know at this point in time, but uh, one thing I wanted to kind of say with this is, so when we're talking about photons, right, we're talking about light, and people say that light behaves as both a wave and a particle, and um, I think that makes sense on the same level as saying that a wave in the ocean is both a wave and a particle. Um, because we're saying water is both wave-like and particle-like at the same time. I feel like it doesn't really make sense to describe it as that. It's not one or the other. It's not both. It's a photon is a particle. Light is particles. But in general, a wave of light is not a single photon, but is a mass of photons being sent out in a wave-like manner. And so when we see a wave in the ocean, right, that wave is made up of individual water molecules, but the water molecule is not a wave on its own. It's just a molecule, right? And so it behaves like a wave in mass, right? When there's a lot of water molecules, it behaves like a wave when energy, like it behaves as a wave when it's given energy, but it's not a wave on its own, right? And so when you look at a photon and you look at light, it's the same thing. This photon is not a wave on its own. It doesn't behave like a wave on its own. It behaves as a particle. Because it is a particle, right? And it's not until you introduce a wave of particles that you get a wave of particles. Like I feel like this is really not groundbreaking stuff here. I don't like light is made of particles. It's just a wave of particles. And so I don't think it's quite right to call it a wave. You know, because the properties of the wave is not defined. The way we define the properties of the wave is, its wavelength and its amplitude, basically, and its frequency is what defines its wavelength. And all of that is defined by the energy of the photons in the wave. If you look at an individual photon in that wave, it has all the properties the wave has. Like, it defines all the properties the wave has. So to say that light is a wave is not it's not true. It creates waves. Light creates waves. But that's more just an effect of how radiation works, and a particle is sending out radiation in basically every direction. And it's not just sending out, a single photon in one direction. It's sending out multiple photons, in every direction. And so these photons build up, right? If you blow on, still water, then that builds up little waves on top of the water. So then, would you say that the water is now waves? So then, when there's no waves, it's no longer. The water is still waves. Like I don't know if that. I don't know if that makes sense. What I'm trying to say is that saying light is a wave is just a way to help us understand what's going on, but it is not the actual truth. Because what's really there is individual particles that as a whole create a wave. And so I don't know I don't know what I'm really trying to say here. It doesn't matter too much. I just want to make it clear that a particle, that like a wave, the wave, I'm just trying to make it clear that light is individual particles, and it is basically points of high energy and then points of low energy, because all the energy on either side of this wave of particles is in the particles, right? The energy has been pulled in to the particles. So we get hit with, no energy, energy, no energy, energy, no energy, energy, kind of hitting us. And the amount of energy in the photons allows them to travel at faster speeds. And we know that when this happens, what's the term? It scrunches up, right? It compresses. I can't think of the technical term. I think it's something along those lines, right? And so that is why higher energy photons have, shorter wavelengths. It's because they are traveling at a faster speed because they have more energy. And the wavelength gets longer as the energy, decreases. And as we know, it travels slower. So basically what I'm trying to describe here is that the wave is formed by the particles. The wave does not exist without the particles. The particles are just there doing their thing, right? And them doing their thing creates the wave that we observe. And my camera is going to die, so I'm going to say that I should call it there and say peace out.